Okay, so I would like to thank Nikolai for accepting our invitation to speak for our DaSSWeb series seminar. Nikolai has a PhD in economics from the University of Michigan, and he has been with Banco de Portugal since 2008 in the Economics and Research Department. Nikolai, thank you once again for accepting to talk to us, and you may start whenever you feel like. Thank you.
Right. Thanks, Maria, and thank you for inviting me, and thank you all for coming. So this is the views that I expressed today are my personal views and not those of Banco de Portugal or the Eurosystem. It's a requirement for us to say this. So as the title suggests, this is a paper about latent variables in dynamic economic models. And in the paper, I developed a new spectral decomposition of the information about such variables, the purpose of which is to show where in the spectrum information about latent variables in structural macroeconomic models come from. For example, how much information comes from the lower end of the spectrum, the business cycle frequencies, or the high frequencies. Why is this useful? It's useful because it can help making the estimation of structural macroeconomic models much more transparent than it usually is, by making the estimation of those latent variables in such models much more transparent. The lack of transparency is a very common criticism of structural estimation in economics in general, and also in macroeconomic, in empirical macroeconomics as well, in particular. Structural models are usually quite large and complex. They're different. Estimation is non-trivial. It's often difficult to understand what's going on. So they're often described as black boxes. So this is in general in economics. In macroeconomics, it's very common for researchers to introduce, especially in business cycle research, it's very common for researchers to introduce new types of shocks which are not very familiar and not well understood, that are more exotic, and to find that those shocks play an important role in driving business cycle fluctuations. So this is a very common theme in business cycle research, and it is often not easy to see what identifies these shocks, like where in the data information about the shocks come from, especially again when there are shocks which are not very well understood and not very familiar, which there's incentive in this literature to do that, to argue that there is some other shock that no one has thought about in the past, and to then show evidence that those shocks are important. But it's difficult to understand what identifies and what are the sources of information about those shocks. And so the analysis I develop in the paper can help answer those questions about shocks and more generally about latent variables. And therefore it makes that aspect of estimation of structural macro models much more transparent than it typically is. And transparency in structural estimation is useful because it can help us understand, or at least get a better understanding of what drives the estimation results. It can make it easier for other researchers to assess the credibility of estimated models, and therefore makes it easier to criticize models by if there's some issues or some implications, some properties of estimated models that are not seen as very, very credible or very plausible. By making estimation more transparent, it's easier to reject models which are not very good, when we have understanding of why the results are the way they are. So that's the argument in general for increased transparency in structural estimation. Is there is a concerted effort to improve transparency of structural estimation in general, and so this paper is one contribution to that literature. So this is in short what the paper is about and why it is interesting or important. Next, I'm going to tell you in more details what what precisely I do in the paper and how, starting with a few basic definitions. First, for those of you who are not familiar with the terminology, what are latent variables? So these are variables which are treated as unobserved when a model is estimated. Typically, these are variables which represent purely abstract concepts, theoretical concepts that we don't have data on, that are not measured by a statistical agency. So there's no data that we can use to represent them in estimation, and therefore they have to be treated as unobserved. It's also quite common in empirical macro to treat as unobserved also variables for which data actually exists. So data is left out of the estimation. The most common reason is to avoid the so-called stochastic singularity problem, which is the problem of having, in a given system, having larger number of sources of information than the number of sources of randomness. In that case, the covariance matrix is singular, and which is the reason why it's called stochastic singularity. And it's impossible to estimate these models with maximal likelihood. So that's the common practical reason why in some cases, even if data is available, it is left out for some variables from the estimation. So the point here is that latent variables don't have to be only variables that are unobserved to everyone. They can be unobserved or treated as unobserved in a given estimation, and that's in some sense could be a choice of the researcher. There could be other reasons, such as here I mentioned model validation, which is so some variables may be left out of the estimation, and then the model predictions for those variables can be compared with the actual data to see how well the model captures those variables or predicts those variables. So these are some examples of latent variables that are important in macroeconomics. They're variables like potential output or output gap, natural rates of interest, unemployment, and so on. There are also expectations in general, in particular inflation expectations. And because expectations are unobserved, this also makes the real interest rate, which depends on inflation expectations, makes it also unobserved variable. I already mentioned shocks. There's a plethora of shocks in both theoretical and empirical macroeconomics, technology shocks, preference shocks, policy shocks, financial shocks, and so on. And those are typically treated as latent, as unobserved, and so on. So this is just some of the many examples of latent variables that are relevant in macro. So here in this definition, I wanted to emphasize a couple of things. The first one is that latent variables are variables. In particular, they're not parameters. So estimating variables is quite different from estimating parameters. So that difference should be kept in mind. So some people are not even comfortable with saying estimating latent variables. They prefer other words. But I'm going to use estimated or estimating with this caveat that it's different from estimating parameters. It is in a frequentist framework. In Bayesian framework, perhaps they're the same things. The second point is that there is always a model. So it's a variable which is treated as unobserved when the model is estimated. We always need a model to estimate, with the caveat I just made, to estimate the latent variable. We can, of course, describe them in words verbally. We can describe what potential output means or natural interest rate. But in order to learn anything from data we observe about these variables, we need a model. And in this context, what is a model? Well, a model is basically what describes the relationship between what we observe on one hand and what we are interested in learning about. So that's kind of what the model does in this context. A definition of not a definition, but a description of a model that I like is we can think of a model as a blueprint for simulating data of the model variables. So if we have if we're able to write down a computer program that we can then use to simulate artificial data, then we do have a complete description of a model. If there's something that we don't know, then perhaps there's just a partial model, but not a complete model. Yet another definition that I like of a model is simply a joint probability distribution of the model variables, right? And that distribution doesn't have to be explicit in some explicit known family form, but as long as we have enough information to simulate data, then implicitly we have a distribution of a joint distribution of the model variables. So if F denotes the joint distribution and X and Y are respectively the observed, the latent and observed variables, then a model is simply a joint distribution of X and Y, is F. And then, given that that definition of a model, our knowledge about X, which is what we don't observe, given the model and given the observed data Y, is simply the conditional distribution of X given Y. So this completely describes our knowledge of X given what we observe and given and conditional on the model that we work with. So estimating latent variables is, in a sense, it's basically characterizing this conditional distribution. Now, what is information? Information is we can think of information as the reduction of uncertainty relative to some base level of uncertainty. For example, if we observe variable Y and don't observe variable X, then the information in Y about X can be quantified as the reduction in uncertainty or the reduction in variance when we observe Y compared to when we don't. Right? So if Y is informative about X, then the difference is positive. If Y is uninformative about X, then the conditional and unconditional variance is the same. So in that case, the information is zero. So this is unconditional information. We can also define conditional information in a variable Y1 about X given another variable Y2 as the additional reduction of uncertainty when we observe both Y1 and Y2 compared to observing only Y2. Right? This tells us how much additional information we get about X when we observe also Y1 relative to observing only Y2. Information in the frequency domain, which is relevant given the topic of the paper, is defined in the same way as the reduction of uncertainty. But in the frequency domain, we can measure uncertainty, and therefore we can measure information at any given frequency. And this follows from the fact that the variance of a stationary variable can be decomposed into contributions by different frequencies. So we can measure variance and therefore the change in variance at any frequency, and that would give us the amount of information at a given frequency. In the paper, the particular measures of information gain that I use are the following. This is the unconditional information gain from variable Y with respect to variable X at the frequency omega. This is information gain from Y to X at omega is the reduction of uncertainty due to observing Y at that frequency as a percent of the unconditional or prior uncertainty about X. So here uncertainty in the frequency domain is measured at a given frequency is measured using the spectral density of X at that frequency. And similarly, the conditional spectral density of X given Y at that frequency. So this is unconditional information gain. The conditional information gain is defined similarly as the additional reduction of uncertainty due to observing both Y1 and Y2 relative to observing only Y2 as a percent of the prior uncertainty about X. So this is information gain from Y1 with respect to X, conditional on Y2 at the frequency omega. We can also compute integrated information gain over a band of frequencies. So here omega is a vector. As the integral over that set of frequencies of the frequency-specific information gains weighted with the fraction of uncertainty of the total uncertainty in that frequency band that originates at each frequency omega. So this tells us how much information about X comes from Y at that set of frequency or that frequency band. And we can also then decompose or compute the decompose the overall information gain over the full spectrum. So here omega bar is the full spectrum. We can decompose that information gain as the contributions from different frequency bands. And in macroeconomics, there is a common partitioning of the spectrum into low, business cycle, and high frequencies. But of course, this can be any other partitioning into any other components. So in this case, we have low frequencies, business cycle frequencies, which are usually defined as those with a period between 6 and 32 quarters, and high frequencies. So the contribution of each one of those is simply the information gain at that frequency band, say the low frequencies, weighted with how much of the overall uncertainty, which is the spectral density over the full spectrum, originates. So how much of the overall uncertainty comes from that particular frequency band, say the low frequencies, and similarly the business cycle and the high frequencies. So I'm sure some of you are experts on much more than I am on frequency domain analysis of time series. For those of you who are not, I don't use anything very complex in the paper, and because I'm myself, as I said, not an expert. But here is a kind of very brief information about the necessarily basics regarding frequency domain analysis of time series. So starting point is that any covariant stationary process can be written in this way as the integral over omega, which is defined in the interval between 0 and pi. So these are the frequencies of this expression. And here, what's important to point out is that the cosine and sine deterministic functions, while A and B are independent random variables. So they're functions of omega, but they're also random variables. And so A and B at the given frequency omega determine the contribution of that frequency to the variance of Y. And in other words, it determines how important are cycles with that frequency for Y, how much of the variability in Y is due to that frequency. And so there is this relationship between the value of omega, that is what the frequency is. So small values of omega imply low frequencies, that is, these are cycles that take a long time to complete. These are cycles that move slowly. And large values of omega, these are high frequencies, and they are associated with cycles that move very quickly and complete very fast. And here is a visual representation of frequencies and cycles. So starting with a very low frequency, there's only one cycle that takes 100 periods to complete. If I increase the frequency, we have here 2 cycles over the same amount of time. If I increase it more, we get faster and faster cycles. But in the same amount of time, we get more and more cycles, and at the end, we get 49 cycles that occur or complete in the same 100 periods. So there's this. That's what low values mean slowly moving cycles that take a long time to complete, and high frequencies, fast moving cycles. So here is an illustration of the fact that we can approximate and in fact completely replicate any time series using, if we use sufficient number of frequencies and frequency components. So this is a simulation of an autoregressive process for the one. The data is in red. So blue is starting with only one component, which is frequency 0. So the best approximation we can make of this process with only one component is taking the mean. Right? That's the first component, and it's frequency 0. It simply finds the mean of the process, which in this case is 0. If I add another component, we get this best approximation now with only 2 components. But if I continue adding more and more components, we get closer and closer to the actual time series. And here I finished with 100 components. We get not perfect, but very close approximation of the actual time series. So this is just to illustrate that indeed we can combine harmonic functions in such a way that they perfectly approximate the original time series. And the different frequencies and those components, basically, they reflect how important a given frequency is in getting to that approximation of the original time series. The spectral density function, which I mentioned earlier, it's a function of the frequency, omega, and it measures the contribution of that frequency to the variance of the variable. And again, here is the example with the spectral density of autoregressive process for different values of alpha, the autoregressive coefficient. When alpha is 0, then the spectral density is flat. So each frequency contributes the same to the variance of y. Now, the definition of business cycle and high and low frequencies is shown here in different colors. So when alpha is 0, most of the variance comes from the high frequencies. So here it's 67%. And the low frequencies only contribute 6%. If I increase alpha to, now in this case, it's 0.1, there's a shift towards the lower frequencies. Now, so this is this part, the area in this range. Now they account for 7% or between 7 and 8%. If I increase it to 0.5, they become more important, 18%, and the importance of the high frequencies is reduced. If I go all the way to 0.9, so a very persistent process, almost all of so now only 6% of the variance originates in the high frequencies, and most of the variance is due to the low frequencies. So there is a clean relationship between at least in this process, between the coefficient alpha and the degree of persistence, and which part of the spectrum contributes most of the overall variance of that variable. So in the paper, I illustrate the methodology, this decomposition in a couple of applications. Here I'm only going to show you one of them. It's a model from a recent paper by Martin Uribe in the American Economic Journal of Macroeconomics. It's a paper about the so-called new Fisher effect, which is the effect of monetary policy shocks that move inflation and interest rates in the same direction over the short run. So as opposed to the so-called Fisher effect, which is about the long run co-movement of inflation and interest rates. So in this paper, Uribe looks for evidence for the importance of these shocks that have this effect, new Fisher effect. So he estimates a small scale, what they call New Keynesian model. The model has 7 shocks. 3 of them are monetary policy shocks, 2 preference shocks, and 2 productivity shocks. So these are the latent variables in that example that I'm interested in learning more about. So in the application, I take the model and the estimation results and investigate the sources of information about these shocks in that paper, which is not something that reading the original article we can learn much about. Right? It's left, that part is simply not done. because I guess because we didn't know how to do it. So in the paper, I show one way to investigate and to improve our understanding of those shocks and what identifies them or what is informative about them. So here I'm just quickly going to show you what those shocks do in the model, how they enter in the model equations. So we have a monetary policy rule. This is this is how the nominal interest rate, the policy rate, it changes as a function of inflation and output in the economy. And also it's a function of the lagged interest rate. And there is a monetary policy shock or innovation to the policy rule, which is this term. This is a standard Taylor rule, Taylor type of monetary policy rule. What is less common is the fact that there is a time varying inflation target rate, which is denoted with gamma. So gamma is inflation target, time varying. X is non-stationary productivity process. And this, again, it's a stationary monetary policy shock. So this is the first monetary policy shock in this model. The inflation target is, it has this form. It has two components. One is a permanent component, which is assumed to grow at rate GTM, which is time varying, and a transitory component, which is the second term, which is stationary process. So these are the three monetary policy shocks. The first one is the innovation here, and the shocks to the growth rate is the second, and this transitory component is the third monetary policy shock in this model. So this is the form of the lifetime utility function of the representative consumers in the economy, which to macroeconomists this is probably familiar, but to the rest of you probably not. So here we have two shocks which are shown in red. One is intertemporal preference shocks, which is the shock to the discount factor, which is this psi. And here we have consumption and disutility from working, which is H is the hours worked. And there is a shock to the disutility of working, which is theta. So this is intertemporal preference shock. And both of these are assumed to be stationary processes. Finally, there is productivity shocks. This is a production function. Output is a function of labor, the hours worked. And also it depends on exogenous productivity, which has a permanent component, X, and a transitory stationary component, which is this ZT. So as a summary, the shocks, the 7 shocks, 5 of them are stationary. All of them are assumed to follow autoregressive processes of order 1. And there are also 2 non-stationary shocks. These are the growth rates of which follow AR1 processes. So actually all of the processes are AR1, just that 5 of them are the levels and the other 2 are the growth rates. So these are the sources of randomness. Actually, not quite, but these are the shocks. There are 3 observed variables with which the model is estimated. There is output growth, the difference between the nominal rate and the inflation rate, which I'm going to call a real rate, even though the real rate is usually defined in terms of expected inflation and not inflation. So this is the exposed real rate, R. And the third observed variable is the change in the nominal rate. Now, all of them are observed with measurement errors. So these are also sources of randomness in that system, right? There's 7 shocks and 3 measurement errors. So in total, there's 10 sources of randomness and only 3 observed variables. So here you can see it's the opposite of stochastic singularity. We have many more sources of randomness than observed variables. If it was the opposite, we would get the stochastic singularity problem. Okay, so as I said, I'm interested in the shocks, and in particular, I want to find out where information about these shocks come from. The spectral decomposition these are the results. We have the shocks on the x-axis, and on the y-axis we can see the size of the information gains. So here in this figure, I show with green the overall information gains for each shock, and then the decomposition or the contributions of the low, business cycle, and high frequencies in light green, yellow or orange, and red. Right. So it's immediately clear that there are only two shocks for which there is relatively a lot of information. So these are the intertemporal preference shock and the permanent productivity shocks. So information gains 93% here and 84% here. So the information gain, again, to remind you, it tells us how much of the uncertainty of the prior uncertainties reduced as a result of information that the observed variables provide about that shock. So if we get 100%, this means that there is no uncertainty left. So 93%, it means that there is some uncertainty, but most of the uncertainty has been resolved due to information in the observed variables. So there are only two shocks with relatively large information gains. These are the intertemporal preference and the permanent productivity. The monetary policy shocks, the information gains are much smaller, only 16, 17, 18%, so less than 20%. And the other two shocks, there's less than 2% information gain. So almost all of the uncertainty remains for those two shocks. There's basically no or very little information about the labor supply shock and the transitory productivity shock. So the contributions here, most of the information comes from the low frequencies. 70 out of so out of 92%, 70 comes from the low frequencies. Here it's the opposite. Most of the information comes from the high frequencies. Out of 83, 84%, 42% comes from the high frequencies. Again, high frequencies, business cycle frequencies, and business cycle and low frequencies. Now the contributions from each frequency band depend on two things, on two factors. One is how much of the uncertainty that originates in that frequency band is resolved. So that is the information gain in that frequency band. And second, on how much of the overall uncertainty originates in that frequency band. So this is what we can compare in. So here in this figure, we can see the information gains within each frequency band. Again, so how much of the uncertainty which originates in, say, the low frequencies is resolved due to information in the observed data. And here we can see that there is relatively large amount of information about the low frequencies, not only for this shock, but also for this one and also for this one. So here 95% of the uncertainty from the low frequencies is resolved. Here it's 60, around 70%. Here it's however, the difference between this shock, the intertemporal preference, and the permanent productivity shock is that so the reason why here we get much smaller contribution of the low frequencies compared to here is that for this shock, there's only 10% of the overall uncertainty originates in the low frequencies, right? So even if all of that uncertainty is removed, it still contributes less than 10% of the overall uncertainty. Most of the uncertainty comes from the high frequencies. And that's why the importance of the low frequencies for this shock overall is much smaller than for this shock, right? So even though both of them, most of the uncertainty in the low frequencies is resolved. So there is a lot of information about the low frequencies, but they're different. Their importance is different for these different shocks. For some of them, most of the uncertainty comes from the high frequencies, like here, and also here. Okay, so this is how we can understand how much overall information there is, and what are the contributions from different parts of the spectrum. We can also see how much of the information comes from different variables. So remember that we have 7 shocks, which are on the y-axis here, and 3 observed variables. And we can see how much each variable contributes in terms of information with respect to each shock. And this is what I show in this figure. Here I show conditional information gains. That is the information gained from observing a variable, given that the other 2 variables are also observed. Right? What is the additional information in observing, say, output growth compared to observing only the real rate and the change in the nominal rate. So this is what is shown in this figure. And here we can see that output growth is very informative with respect to the permanent productivity shock, with 83% information gain conditionally. Here we have for the intertemporal preference shock, which was the second relatively well identified shock. We have the real rate being quite informative with 87%. The change in nominal rate is much less important. And here, with respect to the trend inflation shocks, we have again the real rate 13%. The change in the nominal rate is only 8%. Similarly, here we have 16 and 10%. So here we can see which variables are relatively more informative with respect to which shock. Now it's interesting to compare those conditional gains to the unconditional gains, and this is what I show in this figure. And here it's striking. So the darker colors indicate larger gains, right? So it's striking how much larger the unconditional gains with respect to this shock are from the real rate and the change in the nominal rate. So here it doesn't change much. It's the output growth, slightly different number, but still the most important. But here it's the gains are much, much larger unconditionally compared to the conditional gains, right? Here, 27% conditionally and close to 85% unconditionally. Now, the unconditional gain is, if we start from the prior uncertainty, the unconditional uncertainty about the shock, how much that uncertainty is reduced when we observe only one variable, say only the real rate. And the fact that there is such a big difference between the unconditional and conditional gains indicates that there is a lot of redundant information in some variables, right? If we condition on other variables, the gain is small. However, if you compute the unconditional gain, the gain is very large. So that it means that there's some information which is shared, which is in both variables or in several variables. And if we observe one of them, the other one doesn't contribute much additional information. Right? That's what we can conclude by comparing conditional and unconditional gains. And in fact, I developed this measure of what I call information complementarity, which is defined as in terms of the ratio of the joint information gain from 2 variables compared to the sum of the individual gains from each of those variables. So when the joint gain is the same as the sum of the individual gains, there is no complementarity. It doesn't matter if we observe the other one, the gain from observing the other one is the same, right? The joint gain is the same as the sum of the individual gains. So to make this measure being, in the case of no complementarity, to have like a neutral value, I subtract 1. So when the ratio is 1, then subtracting 1 makes the information complementarity between y1 and y2 with respect to x to be equal to 0. And when the joint gain is larger than the sum of the individual, we have a positive complementarity. When it's smaller, we have a negative complementarity. The case of negative complementarity is, I think, the easiest one to think about, to understand. Imagine that y1 and y2 are exactly the same variable. So for some reason, we entered the same variable twice in the model. Then the joint gain from observing both, which is indeed just one of them, because it's the same variable. So the joint information gain is the same as either one of the individual gains, right? So we get 1/2. And in that case, the value of this measure is 0.5 minus 1, it's negative 0.5, which is the extreme case of negative complementarity or redundancy. It indicates, so negative value means there's redundant information. In the extreme case, when there's complete redundancy, in that case, the value is negative 0.5. Okay, and so here we can, this plot shows the redundancy or positive complementarity, indicating those in red when it's positive and blue when it's negative. And here we can see that there is indeed a strong, not complete, but strong redundancy between the real rate and the change in the nominal rate with respect to the intertemporal preference shock. So the negative complementarity is negative 0.38, which explains this in this figure why the conditional gains when we observe say we observe output growth and the change in nominal rate, the conditional gain from observing the real rate is only 27, while the unconditional gain is 85, right? Because this is, in this case, because the change in the nominal rate and the real rate are strongly redundant in terms of information with respect to this shock, right? If we observe one of them, the other one doesn't add much new information. And that's what we can conclude also from here. There's a strong negative complementarity or redundancy between these two variables with respect to this shock, the intertemporal preference. Now we have the opposite, positive complementarity between these variables with respect to the trend inflation shocks, the transitory and permanent. Both of these are positive, and this again, this explains why the unconditional gains are very small. So each variable by itself doesn't inform much these shocks, but the conditional gains are much larger, right? If we observe one of them, then observing also the other provides a lot of information. That's the conclusion here. And now with only 3 variables, it's easy to, even just from this analysis, to figure out those connections, those relationships. But in a model with many more variables, it becomes less easy, and it's easier, in fact, to look at this information complementarity analysis to figure out which variables contribute redundant or synergetic information. That's the, and of course we can look at those in terms of conditional and unconditional. So here conditional means if we look at the real rate and the change in the nominal rate, the conditional would be on the 3rd variable, which is output growth. Right, we have only 3 variables, so any pair of any 2 of them, the conditioning is on the 3rd. Here the results are not very different, conditional on or unconditional. They're pretty much the same in terms of at least the sign and the color. Of course, we can also look at within different frequency bands. And so here I showed you in the full spectrum, whether there's positive or negative complementarity. If we look at different frequencies, sometimes the results can change. Like for example, here with respect to the transitory trend inflation shock, the complementarity between the real rate and the change in nominal rate is negative, right? In the high frequencies. In the business cycle and the low frequencies, it's always negative, and the overall is it's positive, and the overall is positive. But in the high frequencies, it's actually negative. So this means that it depends on which part of the spectrum we're looking at. The same 2 variables can be positively or synergetically related, and or negatively or redundant in terms of information about a given variable or given shock in that frequency band. So I think that that can be, and of course this becomes very complex to this analysis when we have more variables, because then the conditioning can be on 1 other variable, on 2 other variables, on different pairs of other variables, and the analysis can be much harder to understand and to summarize. Here we have only three. So the conditioning is only with respect to one of them, or unconditional. But in general, this is much harder to investigate these relationships. And so I think I think I should finish. I mean, this is another way to present results which I already show you in terms of relative importance, another visualization. So I'm just going to conclude and just so what this paper is about. It's a methodological paper. Hopefully, it will be useful to people who estimate structural models with latent variables, dynamic models with latent variables. The paper is about how to do that, how to find out how to answer this question, what identifies given latent variable in a given model. I think of that as a question about how much information there is about a given latent variable, and also what are the main sources of that information. And those sources can be observed variables. They could also be in time series models, which frequencies provide the most information. And so in the paper, I developed a methodology that can help answer these questions. How much information, and where in the spectrum, or where among the observed variables the main sources of information are with respect to given latent variable. So that's here I have a link to the paper and some other material on my page. That's a QR code. But I'm going to end here, and I don't know how much speaking. I realize that there are many things that I assume as known, like about the application model and so on. But yeah, I hope it wasn't too foreign to most of you.
Okay, thank you very much.